As we move on to discuss limits at infinity and limits of sequences, I think it's first important to review what we know from Algebra 2 about rational functions. Rational functions, as you remember, I hope, whenever you hear the word rational, think fraction. It's f of x equals p of x divided by q of x. Well, we cannot divide by 0, so we know that q of x cannot equal 0. Well, what happens when our denominator is 0? We have a vertical asymptote, a no-fly zone. Your graph cannot cross a vertical asymptote. How about if you can factor and cancel, as we saw with the dividing out technique? You saw that I mentioned anytime you cancel, there's a hole. If you wind up having something like this, x minus 3 times x plus 2 over x minus 3, and we say that this is our function. If you cancel your x plus 3's, then there's a hole at x minus 3 equals 0, so x equals 3. That's the x coordinate of our hole. How would you find the y coordinate? Now, if our surviving function becomes y equals x plus 2, you find the function value when x is 3. Clearly, 3 plus 2 is 5. So we'd say there's a hole at 3, 5 in this case. So vertical asymptotes, wherever our denominator of a rational function equals 0. If you factor and cancel, as we saw with the dividing out technique, we were actually finding a hole there. Cancel x minus 3, then the hole's at 3. 3 what? Well, if this is your surviving function, plug that back in or substitute that into your surviving function to find the y coordinate. A vertical asymptote will be of the form x equals something. It's a vertical line. So if we have a vertical asymptote at 2, we'd say x equals 2, and we draw this no-fly zone at 2. How do we find that? Denominator equals 0. Cancel, there's a hole, find the hole. That's an xy point. Now we have 3 rules with horizontal asymptotes, which will be super important today. If the graph has a higher degree in the denominator than in the numerator, see, that's such a mouthful. I just say, if it's bottom heavy. So what would bottom heavy be if we had something like y equals x squared over x cubed? The degree in the denominator is greater than the degree in the numerator, so we call it bottom heavy. We can conclude immediately that our horizontal asymptote is y equals 0. If the ratios are equal, if we say it's x cubed over x cubed, if I change this up just a little bit, and they're equal, well, then we go to the coefficients of the, we go to the lead coefficients. We look at the ratio. Say it was 2x cubed over 1x to the third. Well, then our horizontal asymptote would be y equals 2 over 1, or y equals 2. So that's what we do if the degrees in the top and bottom are equal. And if it's top heavy, like y equals x to the fourth over x to the third, notice the highest exponent in the top is greater than the highest exponent in the bottom. I should be saying numerator and denominator. We say there is no horizontal asymptote. How do we find a x-intercept? Well, that means we're going to put a 0 in for y. And if we have 0 equals p of x divided by q of x, what would be your next step? Multiply both sides by q of x, and when you do that, you see that that will cancel to 0, and that will cancel to 1. We'll get numerator p of x equals 0. So that's our little shortcut for finding x-intercepts. Y-intercept, if we have f of x equals this function, we're going to find the f value when x is 0. And then at the very end, we pick x and we calculate y. Hopefully, we won't have to do that because we'll have a good picture between vertical asymptotes, horizontal asymptotes, and x and y intercepts. Hopefully, we won't have to do anything more than that. So this is all information found in chapters 2.6 and 2.7. If you don't remember that from Algebra 2, go ahead and read those chapters. So important are these rules for horizontal asymptotes because they have incredible implications to find limits at infinity. So why are we studying this again? Because if you have a limit of f of x as x goes to positive infinity, or limit f of x as x goes to negative infinity, we haven't seen these before, but as x gets very, very big or x gets very, very small, extreme values, 1,000, 2,000, 15,000, 100,000, or negative 1 billion, negative 2 billion. As x gets off the charts either way, what controls the shape of our graph? None but our horizontal asymptote. Hopefully you remember from Algebra 2 that the graph, if you have a graph and you have a horizontal asymptote, the graph can pass your horizontal asymptote, but eventually the graph will settle in. And as x gets extreme, dude, to negative infinity on this side or positive infinity on this side, look what happens to our graph. Our graph will eventually travel alongside of our horizontal asymptote. That's why I say the graph's behavior is determined or governed by the horizontal asymptote. The horizontal asymptote controls the graph at extreme values of x. Where are the values of x extreme? When we take the limit as x goes to infinity or negative infinity. So if we know these rules, then we can figure out limits at plus or minus infinity. If I'm given a rational function, again, a fraction, p of x over q of x, where the denominator doesn't equal 0, we know when the denominator does equal 0, we're talking about vertical asymptotes. Bottom heavy. Take a look at this. I'm looking at the largest exponent, or the highest degree of the numerator and the denominator, because 3 is bigger than 2. Look at, I purposely tried to screw you up, giving you coefficients that are just the opposite. It's the exponents, or the degree, that matters, because we have larger exponent in the bottom than in the top. I call that bottom heavy. And our graph will conform to this line. There is our horizontal asymptote. Bottom heavy, y equals 0. By the way, that's simply the x-axis. Our graph will eventually conform to the x-axis as x gets really big or x gets really small. How about equal? Well, here, our exponent, the degree of the numerator is 5, the degree of the denominator is 5. So we go to the ratio of the lead coefficients, 18 over 6. So y equals 18 over 6. Don't forget, guys, that y equals is just a line. Y equals a number is a horizontal line. So that will simplify to y equals 3. Why is that important? Because as x heads to infinity or x heads to negative infinity, we know y will be going towards 3. Lastly, top heavy. Now look at this. 5 and 3. I'm not looking at 12 and 11, the lead coefficients. I'm looking at the degree. I know that we have no, or not applicable. We don't have a horizontal asymptote. So we say that the graph will increase or decrease without bound as x heads towards plus or minus infinity. So, as a reminder, horizontal asymptotes are important because horizontal asymptotes govern our graph at extreme values of x very big or x very small. So we can use horizontal asymptotes to figure out the limits at infinity.